My name is Michael Slater. I'm a research engineer with Frontier Energy, and we run the Food Service Technology Center, which is the lab that does all of the Energy Star testing for the commercial food service world. Um, so, see if I can also advance these slides.
Hi, Michael. You might want to
Yes.
see if you can change or adjust your microphone because there's a lot of background noise.
Okay.
Sorry about that. It might not be coming through the headset, and maybe it's just coming through the computer microphone.
Sure. Is that any better?
Yes, much better.
Okay, cool. Great. I also need to be able to take control here. Um, all right, great. So yeah, this is going to be commercial kitchen electrification for policymakers. I basically am going to be talking about a bunch of stuff that we've compiled over the last 35 or so years in the Food Service Technology Center, which is going to be a combination of things that we've learned from the lab and things that we've learned from doing field studies, and also just by talking to people in the industry, seeing what works and seeing what doesn't. So yeah, that's me. I'm a research engineer. I have a professional engineering license. So the Frontier Energy team is a fuel agnostic, mission driven team. So the mission is cutting carbon and saving water. And we're talking about electrification, and going all electric is the clear goal for commercial food service facilities, at least in California. Um, One of the ways to help mitigate some of the challenges that people are going to face with coming up with a fully 100% electric kitchen, which are going to be high install costs for changing out entire cook lines, having to get service entrance upgrades, which is, if anybody's ever done construction or a massive retrofit, can be a massive, massive hurdle. And also installing things like new electrical stud panels. All of these things are fairly expensive, and they're going to be difficult for people to be able to do on their own. So one of the things that I'll talk about a little bit is using high efficient gas technologies to basically serve as a stopgap, so that people can start saving carbon without having to completely electrify, using natural gas, essentially high efficiency natural gas, as a crutch to get us between where we are with the industry, which is like 1970s, like bare bones, like not super efficient gas technologies, towards high efficient all electric technologies. So, big picture perspective here is that commercial food service is the most energy intensive commercial end use. Commercial kitchens can use 10 times more energy per square foot than any other commercial space. So when you're looking at trying to save energy in the commercial building stock, commercial food service is kind of an obvious place to start. Food service is a relatively small, but a huge percentage of US greenhouse gas emissions, using about 3% of the total, um, producing about 3% of the total US greenhouse gas emissions. So commercial and residential building stock burns about 13% of the US's natural gas. And commercial food service is the largest single sector in that subsegment. Um, and another sort of challenge for the commercial food service world is just that restaurants are really suffering economically. So most restaurants are operating at a loss. These two colors, the dark green is like now, and the light green is pre-pandemic. So before the pandemic, most commercial food service facilities were making a pre-tax profit somewhere between 6 and 10%, which is definitely enough where people were thinking about expanding, buying new equipment, being able to open additional locations, whatever. But now, 62% of restaurants are operating at a loss or just barely breaking even, which is, you know, these people don't have cash on hand to make big um, equipment upgrades, and also, you know, many restaurants are going to end up going out of business fairly soon. And yeah, very few restaurants, you know, the 6 and 7% at the end of the graph there are actually operating at any kind of a reasonable gain. So essentially, this graph means that while you probably didn't have to worry about your favorite restaurant closing down before the pandemic happened, you probably have to worry about your favorite restaurant closing down now. So we'll talk about kitchen electrification from a technology perspective. We'll talk about challenges, performance, availability, and kind of the reality of being able to electrify. Electrification means all electric kitchens. Some of the challenges for commercial kitchens are that this will require some behavioral changes, especially with the way that people operate with some of their sort of major building systems. And electricity is a much more expensive fuel than gas. So in the Bay Area right now, electricity costs somewhere between 5 and 6 as much per equivalent unit of gas energy, meaning that if you want to make a one-for-one replacement for gas technology to an electric technology, you need to reduce the amount of energy that you're using by a factor of 5 or 6 before you can break even on your operational costs of doing that replacement. So one nice thing about commercial kitchens, as Chef Chris was saying, is that there are many appliances that don't require any kind of behavior change, and also there are just complete, easy one-for-one replacements available. It's maybe 90% of what you see under a hood. The real breakouts that don't have good one-for-one replacements have some other sort of operating differences. So, you know, this would be like changing out a convection oven for a high-speed oven, for example, right? The high-speed oven is highly efficient, works fairly quickly. You know, the high-speed ovens are essentially what you see behind the counter at Starbucks. And you can use these in the back of the house to sort of replace what you would do in a convection oven, unless you're a bakery. But it means that you have to have sort of smaller cooking loads than you typically would for convection, and you're sort of just going to be running a lot more of them a lot more quickly. So instead of like, oh, I'm going to bake a pan of potatoes and that's going to take like 50 minutes in my convection oven, it's going to be more like, oh, I'm going to bake like 10 potatoes at a time. But, you know, in this high-speed oven, it's only going to take like 15 minutes. So there's some slight operational differences that you'll have to take into consideration when doing these changeouts. As Chef Chris was saying, induction is a superior technology to either gas range ovens or electric resistance ranges. There's a slight misconception that creating all electric kitchens requires an all induction kitchen. Just something that we've heard from people. But induction is just one way of transferring heat that happens to work well for range tops. It doesn't happen to work well for things like, you know, griddles or fryers, for example, right? If you have electric resistance running through a griddle top, you still need to get the entire griddle top hot. So even if you've managed to make an induction griddle top, the whole induction griddle top is still hot. It's still giving off heat to the environment and still losing about as much heat as you normally would in sort of an electric resistance mode. So, you know, there's not much of a point of using a more expensive way of transferring heat for that particular technology. But, you know, again, for range tops, it totally makes sense because using induction will actually save you a significant amount of energy based on the way that it works. So there are effective electric appliances that do not use induction. So broilers, fryers, pasta cookers, ovens, steamers, and kettles. If your heating element is designed to heat up a fluid like fryer oil, pasta cooking water, or convection oven air, you don't need to use induction as sort of a general rule. So also to sort of echo some of Chris's points, so can electric equipment keep up? It totally can. Usually electric pieces of equipment have roughly the same pound for pound performance as gas pieces of equipment. So one thing that we do in the lab, we basically do 4 tests on every piece of equipment that comes into our lab. One's a preheat test where we go from an ambient condition to a ready to cook state, where we're measuring the like temperature and energy usage. One of them is an idle rate test where we're trying to figure out how much energy an appliance will use when it's in a ready to cook state but not actually cooking. And then a cook test where we're measuring the cooking efficiency and the production capacity during a cooking mode. So this graph is basically just a straight up average of every appliance that has come through our facility over the last 30 years, where we're looking at what the average production capacity is for griddles, fryers, convection ovens, combi ovens, and steamers. Blue is gas, red is electric, and you can see that basically in every category, the electric is doing about the same as the gas, in some cases slightly outperforming the gas. Efficient electric appliances are highly available, and they've started to sort of saturate the market. There are many different manufacturers who are making induction and other high efficiency electric appliances that are totally commercial ready. And if you look real closely at the bottom middle picture, you can see that there's an induction wok there. And again, to echo one of Chris's points, demand control kitchen ventilation is highly important because you can get a ton of energy savings. Woks are actually the biggest equipment challenge for doing one-to-one gas to electric replacements. People may be familiar with some of the issues that have happened around woks in general and being able to do natural gas bans in different localities. And one of them is just that gas woks you can control by using your knee to adjust the input rate of the gas under the wok. And so having an induction wok that works a little bit differently, where you have to manually, like with your hand, control the amount of heat that's going into the pan. It presents a little bit of a cultural difference in how you're cooking your food. And so there's been some pushback from typically Asian food places, Asian restaurants that use woks about using electric woks instead of gas woks. And so, induction woks being so much more efficient and being a little bit easier to control than your standard electric resistance woks has sort of started to allay that challenge a little bit. This is a story that is still kind of going on, so stay tuned. So we'll go into the economics of doing all electric kitchens. So I want to talk about equipment costs and energy costs, essentially as a capital expense and an operating expense. For all equipment, the capital expense for gas is about the same as the capital expense for electric, and the operating expense for electric at the time that we made these slides was about 2 times greater than gas. So that's electric appliances are, as a rule, more efficient than gas and use a little bit less energy in general, but electricity is still more expensive than gas. So you still end up having a higher operating cost for electric appliances compared to gas. So for induction, the capital expense is like 2 to 3 times greater than gas, and the operating expense for electric is about the same as gas. So looking at an entire cook line, this is sort of a mock base efficiency cook line where we're using a couple of gas combination and convection ovens, a gas griddle, a gas range oven, and a gas stockpot burner. And then we're using an electric steamer and an electric holding cabinet. So for the standard throughput that you would see for a facility that's using this cook line, this cook line is going to emit about 35.2 metric tons of CO2 per year. Its fuel cost is going to work out to be about $25,000 a year. So this is kind of like the business as usual. Like this is sort of what's on the market. People are using like low efficiency gas and some low efficiency electric equipment, and paying sort of through the nose for their fuel cost. Just by upgrading to efficient appliances and not changing fuel types, the CO2 can go down to 24.5 metric tons per year, and the fuel cost can go down to $16,000 a year, which is a savings of about 10.7 tons of carbon and $8,000 of operating costs a year. So this is just, one-for-one replacements, no change in fuel type. This doesn't require you to upgrade an electrical panel or anything. You can still save carbon and save some money by doing this. The sort of next step in going towards a more efficient and more electric kitchen is by changing out some appliance types. So instead of using a convection oven for doing baking, you can do all of your baking in a mini rack oven, which is a little bit more efficient. And then you can replace your double stack combi with a high efficient single stack electric combi. Replace your low efficiency gas fryer with a high efficiency electric fryer with automatic grease filtering, and also add a high-speed oven to sort of pick up the slack for anything that got missed in this transition.
Hey, Michael, you've got about 2 minutes left.
Man, okay, so going to the hybrid kitchen of the future cook line, making a couple of changes, you end up saving about 22.7 tons of carbon and about $17,000. And then going all electric with all of this, you've managed to save 33 tons of carbon and about $5,000 in fuel costs, again, because electricity is so much more expensive than gas. But the all-electric kitchen has saved almost all of the carbon compared to the business as usual case. So that's kind of the reason that we want to do this, right? That's the environmental drive to go all electric, is that it saves, to be glib, I guess, tons and tons of carbon. So big picture comparison, the cost versus carbon dioxide. Going from a base efficiency in blue to the kitchen of the future in red on the right, you're still saving some money, but you're driving down your carbon dioxide so much. The electric kitchen of the future really is going to be what people are going to go towards. But as we figure out how to do this in sort of a more cost-effective way, more people are going to end up benefiting from being able to go to high efficiency and hybrid kitchen of the future models. You get some labor and maintenance savings. I'm going to blast through all of this to get to the end. The reality of going all electric is that energy efficiency is the most crucial component of decarbonization and electrification. Most people aren't going to be able to totally electrify for a variety of reasons right now. And so being able to apply energy efficiency is really going to be the first step in getting most restaurants there. And lastly, there are some PG&E resources, including energy surveys, design guides, and rebates available on the California Energy Wise website. and the Food Service Technology Center does demonstrations. So anybody who's running a kitchen who wants to know how any of these technologies work, including induction, can come into our facility and try new pieces of equipment with their own food stock whenever they want, as long as they're a PG&E customer. And the California Instant Rebates Program is a great way to go efficient without having to spend as much money. It's all a downstream service, so all of this is available to commercial kitchen customers at the point of sale. Finally, everybody should try induction cooking at home. It's awesome. Please feel free to click this QR code. PG&E is running a free induction cooktop lending program where you can try out an induction cooktop at home for 2 weeks free of charge. They'll send you the cooktop, they'll send you the pan, and you can see how it works. That's it for me. Thank you very much. I'll take questions at the end. And yeah, didn't realize I was going to go so far over. Thank you.